So now we're going to continue talking about equivalence classes. So we're going to look at an example here. Let's say my set A consists of the elements A, B, C. What I want you to do is consider the equivalence relation, and that equivalence relation is going to be R, consists of AA, AB, BA, BB, and CC. And I want you to determine the distinct equivalence classes So you're going to start by taking elements out of A. Let's start with our first element, A, and we're going to look at the equivalence class for A. So remember, this is all the elements X and A, where X is related to A. So write down all the elements that are related to A. That would be A and B. And now you're going to repeat this for B. Again, this is all the elements from our set A that are related to B. So if you look back at R here, the only elements related to B are A and B. So the equivalence class of B is AB as well. And then finally, my last element in A is C. The only elements related to C are C. So this is, again, all the elements from A where X is related to C, but there's only one element. It's the set C. So two of our equivalence classes turned out to be the same. If you look back here, the equivalence class of A and the equivalence class of B were identical. So there are only two distinct equivalence classes. So the first one is the equivalence class of A and B, which are the same. It's the set AB. And then my second equivalence class, which is the set C. So here I have two distinct equivalence classes. But one thing I want us to discuss is what happened in this last example. Notice that we saw that the equivalence class of A was equal to the equivalence class of B. And so what we can do is we can ask, why was this true? Why were the equivalence classes the same? Well, it's because if you look up here in my relation, A and B are related to each other, right? So this is true I'll say this is true since A was related to B. And so you might ask, does this always happen? If A is related to B, are the equivalence classes of A and B always the same? And the answer is yes. And that's this theorem from your book, Theorem 9.8, says just that. It says let R be an equivalence relation on a non-empty set A, and let A and B be elements of A, then the equivalence class of A is equal to the equivalence class of B if and only if A is related to B. So the only time I get the same equivalence class is if my two elements are related to each other. If A is related to B. So you might ask, do the equivalence classes have to be equal? Could they have terms in common but not be the same? And the answer is no. They always, if they have anything in common, they have to be equal to each other. So that's this corollary 9.9. And I'll write what it says. It says let R be an equivalence relation on a non-empty set A, and let A and B be elements of A if the equivalence class of A intersected with the equivalence class of B is not the empty set. So these two sets, if they have something in common, then turns out that they're identical to each other. So either two equivalence classes are disjoint, so they don't have anything in common, or they're identical to each other. Those are the only two options. Now, I'm not going to go through the proofs of these, but if you're interested, the proofs are in your textbook.